Good morning friends. Today we are going to design and simulate the CMOS layout of 2:1 multiplexer using logic gates as well as transmission gate. Okay, means we are going to design the 2:1 multiplexer in two ways using the traditional CMOS logic gates and transmission gates. For this purpose we are going to use the technology either 65 nanometer and 120 nanometer technology. Now I will show you using the 65 nanometer technology, assuming this capacity load of 0.001 picofarad. Now what are the learning objective? Learning objective is to design and verify the layout of 2:1 multiplexer using logic as well as transmission gate for specific technology for assuming the load capacitance and effect of load capacitance. Again, second is to understand the layout software for designing of CMOS circuits, and third is to calculate rise time, fall time, power consumption, and 2:1 multiplexer design. Calculate the area of 2:1 multiplexer using logic gates as well as transmission gate, and effect of transmission gate instead of logic gate design. Okay, learning objective, outcome. After performing this practical, you are able to design and verify the layout using logic gates as well as transmission gate and effect of load capacitance as well as effect of using the transmission gate on area you will understand. Okay, what do you mean by 2:1 multiplexer? All of you familiar. Multiplexer is nothing but multiplexer has many input and one output line. It will transfer one of the many input to the output depending on select line. Here you can view the schematic or symbol of 2:1 multiplexer. It has 2 raised to n input and n output. Here as 2:1 multiplexer has two input means A and B, and output is Z, and select line is S. Depending on select line, when select line is 0, input A is transferred toward the output. When select line is 1, input B is transferred toward the output. Hence here you can see the truth table. When select line is 0 and all the combinations of A and B, when select line is 1, all the combination of A and B, and depending on our output is going to be transferred. Okay, from this truth table we have obtained the expression Z is equal to A into S bar plus B into S. Now if we simplify this equation for drawing the CMOS layout, Z is equal to A into S bar plus B into S. First of all we will double bar it, then solve the first bar by using the De Morgan's law. A plus B bar is equal to A bar dot B bar, hence A into S bar into B into S bar. Again we will solve this. AB bar is equal to A bar plus B bar, hence A bar plus S into B bar plus S bar whole bar. Now we can draw this using the CMOS circuits schematic. Here if we implement this circuit, here we can show in pull down network two NMOS are connected in parallel, again having gate A bar and S. Again two NMOS are connected in parallel having gate B bar and S bar, and both are connected in series. Here you can view. बाहेर जातो तू, जा लवकर बाहेर, दरवाजा लाव. तू खेळ नीट. आता येऊ नको इकडे. लावून घे बेटा, जा जा लवकर. Here you can see A bar and S, these two NMOS are connected in parallel, and B bar and S bar are connected in parallel, both are connected. Now exactly opposite structure you can see in the pull-up network, where PMOS A bar and S are connected in series and B bar and S bar are connected in series, and both are connected in parallel and connected. Sources are shorted together and connected to the VDD. Okay. Now first of all we will draw the layout of this. Okay, and then we will move toward the layout using transmission gate. Now open the microwin software. Okay, now first of all draw the N-will. First of all we will draw the pull-up network. In pull-up network it consists of PMOS device, hence we have to draw the 4 PMOS devices. Okay, in for that purpose first of all we have to draw the N-will. Okay, in that anvil we have to draw the P plus diffusion material, then 4 polysilicon layer. Okay, middle layers are nothing but A bar and B bar, and outside layers are ES and ES bar. Okay, and then we will make the connections. Start with this. Select the anvil. Then P plus diffusion material. Then check the DRC. Okay, this distance should be minimum 6 lambda. Okay, then N plus diffusion. Okay, now I will increase the size of this again, increase the size of this, and increase the size of this for connections. DRC. Okay, okay. Now, after drawing this, now A bar and B bar source are connected to the VDD. Okay, and S and S bar drain are connected, shorted together toward the output. Okay, and these are internally connected, means A bar drain is shorted to the source of S, and B bar drain is shorted to the source of S bar. Okay, we will make this connection in this way. Okay, we will take the metal A bar and B bar source are connected to the VDD. Okay, first of all we will check ERC, and after that this A bar drain and S source are shorted together. No need to put a contact here, as the same material we are going to use. And last connection we are going to use shorting of this drain. Okay. First of all, we will draw the all connection, then put the contact. Okay. After this connection completed, now A bar and S drain are connected together, and the edges are shorted. Okay. Here you can see how to make this connection. To make this connection, okay, this is a S and this is the A bar. The source and drain are shorted to and connected to the output. Okay. After that, to make the connection, this source of S and source of A bar are shorted together, and again these are shorted to the B bar and S bar drain. Okay. Now to make this connection, okay, this is the first. Okay, to make this connection in this way. First of all, we have shorted this, and then we will short this. Okay, now put the contact, upper side P contact, P to metal, lower side N contact, unit, then VDD, and then ground connection. Okay, all contacts are connections are completed now. Okay, now now to generate the A bar, B bar, and S bar, we require the three inverters. Okay, now let's see how to make connections, how to complete this. Okay, we have to put these three inverters. Here we have to draw one inverter yes, then output of yes inverter, inverter output yes bar is connected to the yes bar line. Okay, these are the A bar and B bar. This is the A and this is the B. Okay, now here we are using the ready-made inverters instead of drawing the every time. So we are drawing to there. Here you can see the device, first device, MOS generator. Here MOS generator, here MOS device and double plate. Okay, here I will use the NMOS device, generate the NMOS device here. Okay, I will move this element downwards. Okay, after that MOS generator, PMOS device, generate the device. Okay, I will move this device. Okay, then connect the polysilicon material together. Okay, then connect the drain. and connect the VDD here. Again connect the VDD to the veil, connect the ground, okay, connect the input. This is the yes. Okay, and output. Okay, now I will copy this material 3 times so that I can generate the 3 inverters. Okay, this is the yes. Okay, this is the B, and this is the B bar. A. Okay, now we have to make the connections. This is the A bar, this is the B bar. Okay, output of A is connected to the A bar, means we have to stretch this. Okay, first connection. Output of A is connected to the output of inverter is connected to the A bar input. Okay, then this is the yes output is connected to the S bar. Okay, this is A bar, B bar, this is yes, and this is S bar. Stretch and move. This is yes, output of yes bar like this. Here you can view. Okay, last connection to the yes bar. Okay, S is connected to the S input and S bar is connected to the S bar. Okay, inverter output connected to the S bar. Now again we have connected A bar. A bar input is connected to here. Now only B bar is remaining. Okay, B bar is nothing but this. I will stretch this. Okay, then I will connect this polysilicon from here. Stretch this. Okay. Now put the contact here, metal to poly. Okay, we have to increase the size. Okay, now we can put the metal to poly. Metal to poly. Whenever the metal to poly, we can connect this. Metal to poly. Metal to poly. Okay, completed. This is the S bar connection. This is the B bar connection. This is the A bar connection. Okay. Now anything is remaining. Okay, overlap of this material. We will. I will delete this. Again, draw this. This is n plus 2. Okay. Now how to do this? Here we have to increase the size. Okay, we will resize it again because of small size. We cannot. I will delete this first of all. Okay, we have resize all the connections. Okay, and remake all the connections by because of some lambda rules violations. Okay, still some violation in their rules. One lambda. Okay, we will delete this, and again we will make the connection. Sorry. Okay, now to put the contact poly to metal here. Okay, save the design. Okay, now everything is completed. This is the inverter. Input is yes, S bar, output is connected to the S bar. Okay, the yes is connected to here. Inverter to generate the A bar is output of the this inverter connected to A bar. Inverter to generate the B bar. Okay, B bar is connected to this third. Okay, VDD and supply are already okay. Okay, once again make the DRC, check the DRC, no violations. Okay. Now we will somewhat change the, it will make some faster. Okay, first of all we will check and then we will see the result and then we can see ABS. Okay, now here where is our output? We have to generate see the observe the output at this metal connections. We have not put here symbol visible node and here we will put now visible node. Okay, this is the output. Okay, save the design again and now you can see the result. Okay, this is the A, this is the B. Okay, now depending on your select line, if select line is 0, A is selected. Okay, this is the select line. Suppose from here we can observe select line is 0. Now what is the value of A? Value of A is 0. Okay, select line is 1 at that time. What is the value of B? 0. After that 1. Okay, now again 0 and then it will become 1. Okay, now we will change the frequency, means we will get slower of A and B. We will get slower unit, slower. Okay, again I will make slower A 2 times, slower. Okay, and if I will run this, okay, here you can observe the output again. Yes is 0, A is selected, A is selected. Okay, take 1 minute. I will make the yes against very slower. Means you can observe the output correctly. Okay, now here you can observe. When yes is 1, it follows the B. Okay, means 0 1 0 1 0 1 0 1, and when yes is 0, it will follow the A is 0. Okay, when yes is 1 means it follows the A and B. Again you can make the A somewhat faster compared to B, then you will get the again variation in the output. Faster assign, again you can see the change in output. Okay, now when yes is 0, it follows the A, means 0 and 1. This you can see 0 and 1. When yes is 1, it follows the B, means 0 1 0 1 0 1 0 1. Again yes is 0, it follows the A, 0 1. Okay, in this way it will act as a multiplexer. Now again we have to note down the reading of rise time and fall time. Rise time is near about 13 picosecond and fall time is near about 15 picosecond. It is going to be vary depending on when input is A, when input is B. For when input is A, it will 15 picosecond, when input B it is 28 picosecond. Okay, you can note down this reading, and power is 43.69 microwatt. Okay, now next is you have to measure the area. Okay, you can make smallest design, measure the area so that we can make the scale correctly. Okay, Okay, 0.200 micrometer, and width is and length is 8.70 micrometer. Okay, you can multiply this and calculate the area. This is the 2:1 multiplexer design using CMOS logic gates. Means logic gates, using logic gates. Now we are going to design a circuit for 2:1 multiplexer using the transmission gate. Now before going to design this, let's see what it means by transmission gate. Transmission gate is a CMOS circuit itself again. Okay, transmission gate has three input, three ports. One is the input, second is the output, and one is the control signal. Now this, depending on the control signal, transmission gets activated and it will transfer the input toward the output. Means it passes the input toward the output. Okay, now when this control signal, suppose this control signal is A, and when this A is equal to 1, at that time what happens? Lower side is a NMOS and upper side is a PMOS. This NMOS and PMOS are connected in parallel way. In transmission gate, PMOS and NMOS are connected in parallel. Hence, when A is equal to 1, NMOS gets activated, and A bar is 0, 1. As A is 1 means A bar is 0, means this PMOS again gets activated. Means both gates are P channel MOSFET and N channel MOSFET gets activated, and this switch becomes on, and whatever the signal provided at the input, it will transfer toward the output. Okay, this is the functionality of transmission gate. Now let's see how to design the transmission gate. Sorry, 2:1 multiplexer using the transmission gate. Now this is the circuit diagram of 2:1 multiplexer using the transmission. It uses the two transmission gates. Okay, the input to the first transmission gate is the input 1, and input to the second transmission gate is the input 2. Okay, and now in between the control signal we have connected the inverter. Okay, this control signal, as it is connected to the NMOS of second and PMOS of first, and inverted output is connected to the PMOS of second and NMOS of first. Okay, now what happens when this control signal is 1, at that time lower transmission gate is activated, because when control signal is 1, NMOS is gate input of NMOS is 1, and inverted output 0, means PMOS is again 1. And this switch is becomes activated, and this switch becomes inactivated. Hence input 2 is transferred toward the output when control signal is 1. When control signal is 0, upper side transmission gets activated and lower side transmission get deactivated. Hence input 1 is transferred to the output. This is the functionality of 2:1 multiplexer using the transmission. Now our aim is to design the to draw the layout. Okay, this is the layout, sample layout. First of all, we will see how to draw this. Okay, first of all, draw the N well. In that N well, draw the P plus diffusion material. Then after that, draw the N plus diffusion material. Then parallelly connect the source and drain. Okay, this is the source and this is the drain. Source is has provided the input 1, and drain is from drain you have to take the output. Now similar way you have to draw for second transmission gate. Then short the drain of both transmission gate and take the output. Now for input providing, okay. Now here input, first for to provide the input we have to first of all draw our inverter. In that inverter, uh, control input is nothing but your control input is provided to the NMOS, PMOS of first and NMOS of second, and output of inverter is connected to the NMOS of second and PMOS of first, NMOS of first and PMOS of second. Okay, this way you have to generate the transmission gate. Let's see how to draw this again. Okay, I will take a new design, new transmission gate. No. Okay, let's start with this. Open the palette, Enveil. Okay, Now connect the source and drain using metal. Okay, I will reside this. Okay, put the material upper side E plus sorry contact, upper side E plus contact, lower side N contact. Okay, now still up till now we have completed. Okay, and from here you have to take the input, and from here you have to take the output. Okay, now I will copy this. Okay, now I will short the polysilicon of as this what this connection tells us. The connections tells us that the gate of NMOS and gate of this PMOS shorted together. Now we will make this connection by using polysilicon layer. Okay, in this way we can check the DRC. Okay, now here you can see how this connection is formed. Okay. We have connected this. Again we have to draw one inverter. Now draw the inverter again well. You can take ready-made inverter also. Huh? Ready means by using the MOS generator also. But here we will draw the. Provide the supply. Then contacts, upper side P contact. Okay. Now we have to make these connections. Gate. insert this output. Okay, now provide the supply here. VDD, again VDD. Okay, now input 1, input 2. This is the input 1. Input 2. Now here you can observe we have make all the connection, input 1, input 2. Okay, now we have to provide the control input and we observe the output. Okay. This is the control input. Control input. Okay. Control input and output of control input is connected to the here. And we have to make the meter to poly contact here. This is the control input. This is the control input output. Means inverter output is connected to the middle, and the control input is connected here. And here we have to observe the verify the output here. Okay, completed. You can see we have completed. We have connected the input 1, input 2. We have connected the control input, output of control input, and we have verified the output. Save this design. Okay, and then we can run. Okay, now this is the control input, means select line. When select line is 0, here you get when select line is 1, it will follow the input 2. Input 2 is 0 and 1, means 0 and 1. Okay, when select line is 0, it will follow the input 1, means 0 1 0 1 0 1 0 1. Okay, in this way you can verify the functionality of 2:1 multiplexer using the transmission gate. Okay, now here you can note down the rise time and fall time. It is comparatively lower compared to the design of 2:1 multiplex using logical gates. Power is also minimized because number of CMOS gates requires number of MOSFETs require are smaller compared to the 2:1 multiplex using the logic gates. Whenever we are going to design the any design, or whenever we are going to draw the layout for or any design using the transmission gate, it requires smaller number of gates, hence area is by default minimized and power consumption is also minimized. This is the conclusion of this design. Okay, and finally also you can verify the layout by using the measuring distance. Okay, again you can see what is the area required by using the scale. Okay, length is 11.400 micrometer and width is 10.25. Okay, this is the area. Okay, in this way we have seen how to design the layout by using the microwind software, how to use the transmission gate for designing of CMOS circuits. Okay, and what is the effect of transmission gates on power and power consumption and area of CMOS circuits. Okay, thank you.